Hello, here's some more Chapter 6 homework problems. Here goes. The planet Venus is named for the goddess of love. So how attractive is Venus? If you were standing on the surface, what would be the acceleration of gravity on the planet Venus? We actually have two equations for the force of gravity. We have our good old friend, force of gravity is mass times the acceleration of gravity. We also have Newton's universal law of gravity, G equals mass 1, mass 2, divided by the distance between the centers, the radius squared. Now, one of these masses is the test mass. This is the object we're talking about. And the other one is the mass of the planet, if we're talking about a planetary body. If we set these two equal to each other, the test mass or the mass of the object is on both sides and will cancel. So this equation will simplify down to the acceleration of gravity on any planet is going to be equal to universal gravitation constant, mass of the planet, radius of that planet, squared, if you're, of course, standing at the surface. So the acceleration of gravity on Venus is going to be equal to G, the universal gravitation constant, 6.672 times 10 to the negative 11th Newton meters squared kilogram squared. The mass of Venus, which you can find on that sheet of constants I gave you early in the term, 4.88 times 10 to the 24th kilograms. And then the radius of the planet, radius of Venus, is 6.06 times 10 to the 6th meters, and that is going to be squared. So if we take a look at this, and I'm going to pick up my calculator, 6.672 raised to the negative 11th times 4.88 to the 24th divided by, open parentheses, 6.02 to the 6th squared, close parentheses, and I ended up with 8.87 meters per second squared. Now let's take a look at where the units came from. I have kilograms on the top, kilograms squared on the bottom. So the kilograms on top, we'll get rid of one of those. Meters squared, we'll get rid of meters squared. Now, how the heck do I get meters per second squared out of this? So a Newton on the top divided by a kilogram. Well, a Newton is a kilogram meter per second squared. Divide by means invert and multiply. So divide by multiply by 1 over kilograms. This cancels this. I end up with meter per second squared. And hallelujah, the units actually work. Next problem. The space shuttle orbits at approximately 200 orbited, I guess we don't have space shuttle very often anymore, 250 miles above the surface of the Earth. What is the acceleration of gravity at that altitude? Okay, here's what we've got going on. At this altitude, here's what is up. We have the radius of the Earth plus we have the height of 250 miles, and I want to know at this height, I want to know what is going to be the acceleration of gravity at that altitude. Well, the equation we just came up with in the previous video, acceleration of gravity is going to be equal to G, mass of the planet, times the radius of that orbit, or the distance from the center squared. We know the mass of planet Earth. G is a constant. Radius, we just have to do a little unit conversion, and we can figure this out, and we can solve for AG. So let's do our unit conversion and figure out one value for this entire height of orbit up to the space shuttle or the International Space Station. So the entire radius of the orbit is going to be equal to the radius of the Earth plus the height. Well, the radius of the Earth we know is equivalent to 6.37 times 10 to the 6th meters. Where did we get that? We got that from that constant sheet that I gave you early in the semester. Plus the height, 250 miles. Well, you know, you can't mix meters and miles. It's just like, yeah, you just can't do that. So we're going to have to do a little conversion. So I'm going to go ahead and convert 250 miles. Get rid of miles, keep meters. There's 1609 meters in a mile. When I do that, I get 4.02 times 10 to the 5th meters. So I take this and replace that there. So the entire radius of the orbit is going to be 6.37 raised to the 6th plus 4.02 raised to the 5th times 10 to the 5th power. So the radius of the orbit, I get 6. Let me get scientific notation here. 6.772 times 10 to the 6th meters is the radius of the orbit. Now that I have that, I can go back and use this lovely little equation up here and the acceleration of gravity. I'm just going to pull that down because I'm running out of space. Acceleration of gravity is going to be equal to G, 6.672 times 10 to the negative 11th Newton meters squared kilogram squared times the radius times the mass. So mass of planet Earth, and mass of planet Earth is 5.98 times 10 to the 24th kilograms divided by the radius of the orbit, 6.772 times 10 to the 6th meters, but you got to square that. So the acceleration of gravity at orbital altitude, 6.672 to the negative 11th times 5.98 times 10 to the 24th divided by, open parentheses, 6.772 2 times 10 to the 6th square, close parentheses, and I got 8.70 meters per second squared is the acceleration of gravity at shuttle altitude. Let's take a look at those units, make sure I'm not making silly stuff up. Meters squared cancels meters squared. Kilogram cancels one of those. Newtons divided by kilogram is meters per second squared. All right, I think I've got time for one more, and so let's try and do 15. White dwarf stars occur near the end of the life of a typical main sequence star like our sun. At that point in the star's life, it is shrunk to the size of the moon, but still contains the mass of our sun. If you could stand on the surface of a white dwarf star, what would be the acceleration of gravity on the surface? Wowza, it's going to be big. So I want to use the same acceleration of gravity equation we have used, where we have found G, mass of the planetary body, radius of the planetary body squared. But we're going to play a little mathematical magic. G is a constant, 6.672 times 10 to the negative 11th, Newton meters squared, kilograms squared. Okay, but we're talking the mass of the sun. If we look on our sheet of planetary data, mass of the sun is 1.991 times 10 to the 30th kilograms. Radius of the moon. Moon has an average radius of 1.74 times 10 to the 6th meters, and we have to square that. So let's go forth and shove this in our calculator. 6.672 times 10 to the negative 11th times 1.991 times 10 to the 30th. Divide by, open parentheses, 1.74 times 10 to the 6th square, close parentheses, equals, I ended up with 4.39 times 10 to the 7th, or 43.9 million meters per second squared. Wowza, that is a large acceleration of gravity. That is a very lot of gravity. All right, that will do, and we will see you next time. Bye-bye.